Hi, and welcome to part one of lecture 5, sample mean, variance, and confidence intervals. We're going to talk today in this first part about the probabilistic underpinnings of our experimentations. And what we do in this lecture, we're not going to talk about the technical ways to manipulate Simio to get this stuff. It's really what we need to know before we start doing that, really. So when we run our simulations in Simio, we generate different performance measures. You've computed some of these now. For example, average time in system or the average of resource utilization and so on. And you'll note that if you change your seed, of course, you're going to get a difference between each simulation run. You're going to get something new because it's a new experiment. And that's sort of the desirable thing. But of course, what that means is that the average, these performance measures are random variables. So for example, the average time in system is a random variable, and it's an uncertain quantity before the simulation is run, and it's going to depend on the inter-arrival and service times, which are themselves random. Okay, so throughout this slides, we're going to let x be the average time in system. This is our example for the slides. But this measure, this random variable that we're using as an example, of course, can be generalized to other observed average performance measures. So the question we have is, can we estimate this distribution of x, the average time in system? And really what we're going to focus on, can we estimate at least the mean and the variance of this distribution? It would be, of course, quite nice to be able to say we could use simulation to somehow get the distribution function. And indeed, there's ways we can sort of get at that using histograms or frequency counts and such like that. But first, we're going to look at getting the mean and the variance. So how do we do that? Well, we're going to have to run the simulation many times. And of course, in later parts of lecture 5, we talk about the technical details of this in Simio. Will be discussed. Okay. But for now, just since we're talking about this sort of in the abstract, let's say that we run the simulation n times. So n is going to be what we use to denote the number of replications we run. For each time, we're going to compute the performance measure. In the case that we're describing, this example, the average time in system. And we'll call that observed lowercase x sub I for this ith simulation. And then we're going to use these n observations to estimate the mean of the average time in system. Okay, so each one is an average time in system, each observation is, and we're going to use all n of them to estimate the mean. Now note that we're going to use capital X sub I, so capital X1, capital X2, ... capital Xn, to denote the random variables that the little xi's are just observations of. They're independent and identically distributed because they're each coming from separate simulation runs. And they have an unknown mean, mu, and variance sigma squared. So if we computed like the expected value of xi, they're all the same. They all equal mu. Once we observe them, once we run it, we're going to call the observations little x1, little x2, ... and little x sub n. And you can think of it this way. The capital X sub i's are the average time in system for the ith simulation run before our experiment. And then the little x sub I is the observation, the actual value that we observe after the experiment. And since we're running the same system and using the same sort of setup, we should have identically distributed variables. So our question is how do we estimate mu and sigma squared, and how do we determine how good our estimates are? For what we are going to end up using is we're going to use these two calculations. One is what we call the sample mean, and the other is a sample variance. And then we're also going to think about the standard error, which is the square root of the sample variance divided by the square root of n. I think the one that's a little weird looking is probably the sample variance. And that's what's called an unbiased estimator of the variance. So here, just note the 1 over n minus 1. Okay, so recall that our capital X of I is a random variable. That means the sample mean x bar, capital X bar, is also a random variable. Again, remember this is before we observe it. We're just thinking of the analysis. And we might want to think, well, what is the mean of that? Is our sample mean, a good estimator? And it turns out if you just apply the linearity of expectations, you can pull out the 1 over n. And then you can also pull out the fact that you're summing them because, again, expectation is linear. And if you think about it, remember what I stated before, this quantity here is just equal to mu. So we're summing up n identical mu's, and we're dividing by n, and of course that just yields mu. So that's a pretty, I hope, common calculation that you may have already seen before. I think you have in previous classes. The one that's a little trickier is the variance, and that's because you lose linearity. So variance of x bar by substitution is just this. And then if we pull out the 1 over n, we actually get 1 over n squared. So then it looks, so then we're just having that summation in there. We can, here we have the variance of x of I. We're just summing that because it's identical. So that turns out to be sigma squared divided by n. Okay. So the sample variance here is going to be s squared, and it's 1 over n minus 1. And basically we use our estimator to get at it. Okay. So we use our sample variance, and we take the difference and we square it. Why this is the unbiased, you should see me if you're interested in seeing that calculation. And what it means to be, if you're curious, what it means to be unbiased just means that this will be probabilistically the same as the true variance. So these will be the same, but there's a slight bias if you took 1 over n. I mean, it looks like you should take 1 over n, but it turns out you shouldn't, and that's because of the way variance is a little different than the expectation. Okay, so the sample variance, so this divided by n, I should say. So this sample variance that we calculate is an unbiased estimator of sigma squared over n. Okay, and this is why our standard error, you'll note, is the square root of that. This is sort of it's like the experimental relationship between variance and standard deviation. Okay, so how good are our estimates? That's one of the bigger questions. Is our sample mean x bar close to mu? Well, if capital X bar were normally distributed, then that would be true. For example, if x1 through x2 plus x3 and so on and so forth is normally distributed, because sums of normal random variables are also normal. It turns out this is going to be approximately true for observations n greater or equal to 30 by the central limit theorem. Note how this is a nice rule of thumb. So we should certainly be running our experiments with at least 30 observations, preferably a lot more. With simulation, we tend to run a lot more. A lot of experts that I talk to typically think of 10,000 or 100,000 as the minimum. But we're going to see today how we can even calculate it and get a sort of a better understanding of what it should be. We will say the 1 minus alpha 100% confidence interval for mu is the following. So just to put this into terms, if you're confused by it, like a 95% confidence interval has alpha equal to 5%, or 5. Okay. It's going to be x bar minus the student t distribution parameter at alpha over 2 n minus 1. This is called the degrees of freedom. And you should just think of this as the observations minus 1. And this is the alpha is, we know that we use alpha over 2 because this comes from the idea that what happens here is we have the student t distribution looks a lot like the normal bell curve. And what we want to get is we want to get this to be representing this sort of 95%, which means this part of the tail is 2.5%, and this part of the tail is 2.5%. So this is going to be our interval estimate for mu, okay, because we're basically, if you think about this, this is the mean minus a thing times the standard error, and the mean, the sample mean plus a thing, the student t thing, times the standard error. So it's actually an interval. And so this is really basically a closed interval that we're estimating using this. To compute the student t distribution parameter in R, you just use qt, and you put in the parameters like this. So you'd put in 1 minus alpha t, and then the degrees of freedom minus 1, or so the observations minus 1. And then what happens when you get over 30 is it starts to look like the standard normal, which is why I can draw that bell curve. I'm going to stop here, and then part 2 is going to be the next part of the slides.